Hey gang, good morning. Say hi so I know who I got. I'm set up in my little 1 meter square studio. Oh, I got a bunch of folks. Good morning, Lara. Good morning, Lola, Errol, and Alicia. Happy February to you all. Good morning also, Louisa, Ellie, Chelsea, Feeny, and Bella. Hope you're all staying healthy and warm and out of the snowstorm. Good morning, Oscar. Nice to have all of you here. Nice to be back. Good morning, Amina. We are just coming in droves. I love it. I got 10 of you, which is 2/3 already. Super. And there's another. So let's see who else we got. Penelope, good morning. Dynamite. Let me tell you what's up. I think this morning we're going to just work through some material and then I'll take your questions on Wednesday on problems on chapter 2 and 3, as it were. So today we're going to do new stuff. So hopefully you had a little tea or coffee, which you can still do. Get yourself awake enough to think about Gibbs free energy. Woohoo! Anybody else coming? Maybe we'll start up. Okay, super. So um, I sent you on the live stream information from the AP College Board website, and the latest is the test will be absolutely normal like last year for the written one. Okay, and the written one, the option is beginning of May. And I don't understand why there's an option at the end of May. I don't quite get that. Maybe it's the one that in case you have two tests at the same time. So the end of May one would be the makeup one, so to speak. Good. There's Antonin as well. Good morning. There's also a digital option you can take, which is in June. And the digital option is not the same length, time-wise, or number of questions. And there's Aiden. Good. Thank you for making it, everybody. So Antonin. Got almost everybody. That's cool. So what I'm trying to say is the digital option, if you're going to do that, let me know. But other than that, I'm going to get all of you ready for the first part of May, the first date we got, early May. So that's my goal. So we got chapter 3 we're going to talk about today. Maybe we'll finish it, maybe not. Chapter 4 is also fairly quick about solubility. 5 and 6 will take a while. Those are acids. And then we got one last chapter on redox, reduction oxidation, which you know a little bit about already. That's the last chapter, chapter 7. So the light is at the end of the tunnel. We'll try and get you there with everybody along. In the meantime, I'll probably schedule another AP classroom quiz, this one on reaction rates. So chapter 2, I think it was, either 1 or 2 in the new book. But I'll tell you more about that on the AP Classroom once I have a chance to make it up. I won't be able to grade your books till I see you again. So just do it all. I'll grade them at some point, but I can't grade them now. That's the way life's got to be. Okay? Anybody else out there? I'm still missing Anne Sophie, and I'm still missing Alex. Okay, Alex or Anne Sophie, you out there? Let me know. Okay, so let's go ahead and begin. So from last time, folks, we had this thing which we called, it's called Gibbs free energy, but let's just call it free energy, and it's delta G. And we said if delta G was less than 0, then the reaction was what? Can you look it up in your notes and somebody just let me know? And Sophia's here. Good. Thank you, ma'am. So just missing Alex. Alex, if you're out there, let us know. Okay, so can somebody punch it in? Thermodynamically favored. Thank you, Chelsea. Third fab. Or if you want to use the what Cheryl uses, and I don't know what the AP is going to use this year, but spontaneous. Spontaneous. In other words, if I light this folder on fire, it's going to keep burning, and that's a spontaneous reaction. It would have a definitely a very negative delta G. Okay. And of course, if it's greater than 0, it's going to be not third fab. It won't be spontaneous. For example, this marker dissolving in water, it will have a positive delta G because it's not really going to happen much. Okay, several of you had that. Good. Thank you very much. Today, let's start out by figuring out how to use a very famous reaction, and it has to do with this. We said to figure out if something's spontaneous or not, it's like a pull between two desires in the universe. One is minimum energy and one is maximum randomness. Whoa, okay, we call that entropy. And the other was called enthalpy, or you and I called it heat of reaction. So to figure out who wins, we have this cool reaction, which you'll use so often you'll know it by heart. Delta G equals delta H minus T times delta S. Now, for grins, we can all make those little zeros. And of course, the 0 means typically like 25 degrees, 1 atmosphere, okay? 25 degrees C, 1 atmosphere. So standard conditions, okay? That's what the 0 usually means. Notice our two desires, enthalpy, enthalpy, and the delta S is entropy, disorder. And notice what's multiplied by the entropy. Well, it's temperature in Kelvin. Makes sense, right? The higher the temperature, the more disordered that sucker's going to be, right? Because higher temperature, things are flying around more disordered. Hopefully that makes sense to you. So the T is attached to the entropy for that reason. Delta G is like, okay, who wins? Is it negative, spontaneous, or is it positive and not thermodynamically favored or spontaneous? Let's use this, okay? So off we go with a little example this morning. So given calcium sulfate, and somebody can type in the formula for that, please. Calcium sulfate, let me know what you think the formula is. Calcium sulfate dissolves in water. So give me a little calcium sulfate formula, somebody. See if you can figure it out because you know the ions. I hope you do. If we were in school, I'd be doing an ion quiz to check that out. But I got to trust you. Calcium and sulfate. Hey, there's a bunch of answers. Thank you, Bella, Alicia, and Amina. And what's good is they got all the same thing, which means they're probably right. So it's 2 plus, 2 minus. So it's calcium sulfate. Now, dissolves in water. You ready? You don't say plus water. Never, ever do that because the water, this is a solid. and the water shows up here. I can make double arrows for grins. The water shows up over here. Okay, it dissolves in water, so it's an ion, and the in water is, of course, aqueous. Why am I emphasizing this? Because it's going to be in chapter 4 as well, and sulfate. So when it says dissolves in water, do not add water. No, I have a student do that every year, and every year I have to give that student 0 points on some quiz or test. Don't do it. It's dissolving. You show that on the product side with the AQ, right? Aqueous, aqueous. I know I probably said that before, but that's my job. All right, why am I telling you this? Because the question's going to be, you know what? We don't have the data, so I got to give the data to you. If delta H equals negative 18.0 kilojoules, and delta S, here, let's make these little circles. Delta S equals point. And is it negative? It's negative. So negative negative 0.1397 kilojoules per mole. Now, often they'll give it to you in joules per mole, and you got to change it, okay? So if find delta G sub 0, okay? That's what we need to do. Let me read those numbers again, in case it's in the blurry part of my studio. So the delta H is negative 18.0 kilojoules. The delta S is negative 0.1397 kilojoules per mole. Righto. Okay, so here we go. You know the formula? Delta G with a 0 this time equals, let's drop in the numbers. I just wrote it up here, so I'll just put a little arrow instead of writing it a second time because I have limited board space. So the delta H is negative 18.0 kJ minus T. Okay, Alex is here. Good. Minus T. What do I put in for T? Somebody help me out. What do I put in for T? And why? Yes, you do know. What do I put in, please, for the temperature? Close, Bella. Try one more time. Yeah, exactly. Right. Okay, so because of the little 0, beep, 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 they're asking for it at 25, and they're not telling you that. You got to know that little 0 means 25 Celsius. Now we got it. Thank you, Aiden. So it's 298 Kelvin times negative times negative 0.1397 kJ. Probably it's per mole Kelvin, to be honest, because the Kelvin's got to cancel. Can I have you guys punch that out? Notice I got a negative and a negative, so that'll just be adding. So multiply those suckers, get an answer, and add it to 18. Let me know what you get, please, for the delta G 0. So go ahead and punch that out. Give me your delta G. Let's have several of you do it so I know we get the same thing. Thanks everybody for participating. It's a good way to wake up when you're sleepy. I'd be sleepy too. You're going to be given these data, by the way. Delta H, if you didn't have it, you'd be given the numbers and you'd get H of the products minus H of the reactants. Same with delta S. If you weren't given it, it would be H of the products minus H of reactants, okay? That's what this would be. And so on. You guys got it yet? Here, punch it out. Hurry up, smell the coffee. So bohm times bohm, and that'll make positive because they're both negative, right? Add it to 18. Let me know what you get. So add it to negative 18, or forget. Well, I'm getting some different answers. So let's have everybody punch it out and round it accordingly. Check it out what I got for numbers. So you should round it as well. So far, I still need some rounding. Nobody's rounded it correctly. Ah, there's a rounding from Ellie. Ellie has it rounded correctly. It should be 3 spots because I got 3 spots here. Even if I add stuff, I want to keep at most the tens place is the rule. So yeah, let's look at that. I still got a couple answers. I think it's 20. Thank you, Alyssa. I think it is, as Ellie and Alyssa got, I think it's 23.6. And it's positive. You know what I'm saying? So if you got a negative, you did something that's wrong. I'm pretty sure it's positive. And the label on it is kilojoules. So let's see if you guys are thinking, can you make sense of this now? So is CaSO4 soluble at 25 degrees C? Is calcium sulfate soluble at 25 degrees C? What's your answer? Prove yes or no. So give me a little guess here. You got a 50% chance, right? So what does this mean? Here's your reaction. Here's your answer for delta G. That delta G tells you what about the solubility at 25 C? Is it soluble? So what's delta G mean? Look back at the start of our class today. Is the calcium sulfate soluble? Okay, Amina says it's not Thurfab, therefore others are saying it's not soluble. And that's right. If it's positive, it doesn't happen. So it's not going to go and become aqueous. It's going to stay solid. So it's not soluble at 25 degrees. See why that is? And that's pretty clearly positive. So it definitely is not soluble. Interestingly enough, thank you. A lot of you figured that out. Calcium sulfate is in plaster. It's in plaster for your walls. So it's probably a good thing it's not real soluble, huh? You spill water on your wall, you don't want it to start falling apart like if it was made out of NaCl. But it's another salt, CaSO4, but it's a very insoluble salt at normal conditions. Cool, huh? It's called gypsum. Gypsum's the mineral name for it. Yeah, what your walls are made out of. Good. Okay, let's continue. So that's using it for one thing. Did I already do that? 6, 7. Yeah. Sorry, my studio's a little small sometimes. Okay, I'm just seeing if you got any questions. And let's continue. It is the smallest whiteboard in the world. Wednesday I may be at school again, so I may be able to broadcast with a real chalkboard or whiteboard or something. I'm going to do something with this F. F is going to be known as formation. Formation. In other words, what happens when certain chemicals form? That's what we're going to consider now. You did this a little bit when you guys talked about the breaking and making bonds, right? Bond energies, when we had an activity on bond energies. So what happens when you form something? In other words, let's take an example here. The delta G of formation for water liquid water, is negative 237.2 kilojoules per mole of water. As a contrast, the delta G of formation of C2H2, which is a gas, is positive 209.2 kilojoules per mole. So what? Okay, well, what does this tell you? So what this means is water, forming water is really spontaneous. Really. That's why we got oceans full of it, right? We got tons of water because the delta G is very negative. Whoa. Water forms spontaneously. Why? Well, it's got low energy bonds. Remember that? Starts high, ends low. Very low energy bonds. That's from a different chapter. But this chapter would say it forms very spontaneously. Low energy bonds. Low potential energy bonds. But the other one is an interesting one. This stuff is called acetylene. And it's what welders use. Welders. It's positive, this one. Positive 209. Positive 209. So what welders use acetylene for their torches. You ever see the blowtorch? And then they weld something or they break open a lock with a welder, right? They melt it. So welders use this stuff. It burns really hot, gives off a lot of energy. But look at it. It's a very positive. So they got it in a big canister, right? Well, that canister's got to be kept cool because if it heats up, it is a bad deal. It is very unstable. So this stuff, because it's positive, is not made spontaneously or thermodynamically favorably. So unstable chemical. Another one probably like that is nitroglycerin. okay? You can't form it easily. You can't form it spontaneously at room temperature. It can only be formed by putting a lot of special conditions to make the stuff and then changing the conditions once you have the product. But this stuff, man, it is really unstable. So it's got to be held very carefully. Okay. Let's talk some other delta G stuff. Okay, so delta G at other temperatures. Obviously, most of the data you're going to get is at 25. What if I have delta G at other temps than 25 degrees C? Question mark. Well, it turns out, gang, and this is kind of a good thing to know, delta S, so I'll say, okay, delta S and delta H values, they change very little with temperature. So what that means for you and I is to get the delta G, you just change the temperature. So just change T, the temperature, in our famous equation, delta G equals delta H minus T delta S. So life is good. If it's not 25, don't worry about it, okay? You just do it like normal, but change the temperature. Oh, it's at 50, so now it's 228 or whatever it happens to be, okay? So just change the temperature. You don't have to change the values. Those remain relatively constant, the delta S and delta H values. Why am I telling you this? Because often you'll find delta H or delta S, the way we've done it often in class, products minus reactants, and that doesn't matter what temperature, you can still use the same data. Okay, I'll shut up now. Let me read your comments, see if you got a question. And yes, Bella, that's right. Negative, it's spontaneous. Positive, it's not spontaneous. That's right. Exactly. Thanks, Amina. Right. Good. Thanks for helping each other. Good. Let's continue unless you got another question. That's PG. Okay, here's an interesting one. Let's use the reaction we just used. And say this. At what temperature does no, we can't do that because it's above 100, so that's not possible. At what temperature? We got to use a different one. At what temperature does calcite or calcium carbonate in American limestone, in German Kalkstein, when does this stuff break down into calcium oxide and CO2 gas? That's a solid. So at what temperature does blah, blah, blah become spontaneous? And we're going to give you some data. I got to give you the delta H is positive 178.3 kilojoules, and delta S is positive 0.160 kilojoules per mole Kelvin. Mole dot Kelvin. Anyway, you get the idea. So that's the important thing, is the number there. So delta H again is 178.3 kilojoules. Delta S is 0.160. So if you want to put a 0 there, you may positive 0.160 kilojoules per Kelvin mole. Okay, at what temperature? So now what we're going to do is, got a question. Yes, thank you, Alex. So Alex has got it. So in the equation, delta G equals delta H minus T delta S. You want the changeover point. The changeover. When does it start going from positive, non-spontaneous to negative, spontaneous? So Alex is right. We're going to put in 0 for this sucker, right? Whoop. And now let's drop everything else in. The delta H we got 178.3 kilojoules per mole. Minus, okay, the temperature is what we're going to solve for, so that's our variable. Let's put that in red. Tricky. So the temperature we're going to solve for, and then that's times my 0.160 kilojoules per mole Kelvin. Good. Can you folks do that? Can you solve for T? And let me know what temperature, at what temperature that becomes spontaneous. I'll do the answer over here. Put a label on it as well, of course. So try and solve for this. But this putting in 0 for delta G is really important. That's when it becomes spontaneous, right at that temperature. And let's see if you guys get some answers. Okay, so find the temperature for us. And throw a label on it, please. Everybody punch it out. If you're not participating, please grab a calculator and do so. You will get more out of the class. And I can't make you do it. So even if you're still in your pajamas, please get your calculator and punch it out, all right? Very important that you do that, so you know this will come back to you easier when you do the problems in the book. Still waiting for your temperatures. You're still punching. Let's do it up. Good, I got one guess. Let's see if some others. And then try and round it. Okay, I got what? How many spots? So round your temperature accordingly. Still got to round it. I got one rounded. And the rest need to round. Thank you, Aiden. Yeah, so round it now. How many spots you got? Here I got 4. Here I got 3. Ooh, you got to round it to the lowest number of sig figs, folks. Right, but round it, because if this is the one where you get the point off for rounding sloppily, did I tell you that? You can't just be close anymore. There's one problem where you absolutely have to have the right number of sig figs on the whole AP. So it's only worth 1 point, but it's 1 point you want to get. And it's not 1114. That would be 4 sig figs. I want 3. Round it. One person had it right. Everybody else had it wrong. 3 sig figs. Round it. Ah, thank you, Errol and others. Now we're getting there. So it's 1110 Kelvin. Okay, that's what I mean. And careful, Antonine, careful. You can't cut off the number. You got to put a 0 there as a placeholder. Okay. Wow, that's really hot. Think about that. So what that means, let's answer the question. At what temperature does the reaction become spontaneous? Temperature at 1110 Kelvin. And look at this. And it's minus T delta S. Remember, delta S is positive. So it's minus T. So it's going to be that temperature or higher. Why higher? Because that would make it even more negative. Because look, there's a minus in front of the T. So that's positive already, the delta S in this case. So see what I'm saying? So you want to say the whole thing, that temperature or higher, that's when the thing will be spontaneous, okay? Okay, thanks, Anthony. Sorry to get on you. Just checking it out. Good, good. Then, another thing you can do is if it's not at standard temperatures or pressures, you can do this. This is an adjustment. Let me change colors. I'm getting bored with myself here. How are we doing? We're doing okay. So adjustment for pressure and temperature. No, pressure and concentration. Temperature we just talked about on delta G. So what you do is you do this. Okay, delta G 0 equals, no, sorry. Delta G not standard, so without the 0, equals delta G 0 plus a correction factor. Ready? The correction factor is R times the temperature times the natural log of Q. Remember, Q is like big K, but not at equilibrium. Remember that? And this, the R we got to use here, I might as well tell you, we're going to use it on the next time I erase here. The R is 8.31, and it's from Pivnert, okay? It's derived from Pivnert. 8.31 times 10 to the negative third kilojoules per Kelvin. And Q, so it's products over reactants, not at equilibrium. Okie dokie. Or as my brother-in-law says, okie dokie smoky. Okay, let's do one. Let's do one. Okay, so everybody got that reaction? We need that sucker. Let me erase the top part. Okay, so example. Let's drop acid. No, let's drop something in acid. So here we go. Zinc solid, pieces of zinc solid, plus the main thing in acid is H2, or sorry, H plus, right? That's what's in stomach acid and everything else. And that's aqueous forms, and I'll just make one arrow this time, Zn2 plus, and that's now aqueous ion floating around, plus H2 gas. Okay, if delta G0 is negative 147.0 kilojoules. And notice I get sloppy here. You ready? Tell you why I'm sloppy. I could write kilojoules per mole, but it depends what I'm talking about. It's kilojoules per 1 mole of zinc or 2 moles of H plus. So I'm just going to write kilojoules to let you know it's with this way of writing the equation. 1 mole of that, 2 moles of that. Okay? All right, so there's my standard delta G. And if delta G equals this, and the pressure is 750 millimeters of mercury, so not standard conditions, and the zinc concentration, Zn2 plus, is not standard. Remember what standard concentration is? 1 molar. So I'm going to give you that this is 0.1 molar, 0.10 molar. And I'm going to give you one more. And the concentration of H plus is also not standard. It's not 1 molar. It's going to be 1.0 times 10 to the negative fourth molar. Huge. Okay, so let's look at our reaction. Okay, so what do we need? We need to have the delta G standard. There it is. R we know. T we know. That's still standard. Natural log of Q. Well, let's do that within the problem. Okay? All right, I'm going to erase everything but the reaction. Actually, I'm going to write the equation above again. And you know what? I used to do this in a longer way. I want to do this as short a way as possible, which a lot of you will appreciate, I'm sure. And because I want you to be able to save time. So check out what I do. So here's the reaction again. I'll write it here in blue. Delta G equals delta G standard with a 0 plus RT natural log Q. Okay. I feel like there's something I forgot. Dang it, there's something else I forgot. Okay, sorry. If you can still fit this somewhere. So these are non-standard, and I'm going to give you that I gave you that already. The pressure of this is 750. Okay, I take it back. Let's get Q first. Q is products over reactants, right? So check this out. I've got Zn2 plus. Remember that? Products over reactants for equilibrium constants? I hope some of you are finishing up that chapter now. Or maybe we long did it. Maybe it's 2 chapters ago. Anyway, times the pressure of H2 divided by the only other thing I got. Look, that's a solid. That doesn't count. So I got concentration of H plus squared. Where am I getting that? Remember, gang, products over reactants, solids don't count. Gases got to be a pressure in atmospheres. So I got to do that now. Here's how we do it. 1 atmosphere has how many millimeters of mercury? Who knows? 1 atmosphere has how many millimeters of mercury? So that's 750. How many millimeters of mercury in 1 atmosphere? Type it in and I'll wait for an answer because I want you all to know that. Yeah, good. Bella, Chelsea, Anthony, good. So 760. So here's what we do. We're going to say, okay, to get Q, let's do the numbers. So we got concentration of Zn2 plus was 0.1 molar. Now I'm going to put in parentheses to show I'm just multiplying. Times, let's take 750 millimeters of mercury divided by what you guys said, 760. We're going to do it right within the problem. Because that's one, then it's atmospheres. You understand what I'm doing? That changes it to atmospheres within the problem. Saves you a little time. All divided by my product, concentration of the H plus. Here it is up here, 1.0 times 10 to the negative fourth molar. That sucker squared. Whew. Okay, so I need an answer from one of you. So what's Q? So let me pause and have you guys get that. And in the meantime, yeah, we can start writing out this for everybody else. Okay, so waiting for an answer for Q from some of you here. So please multiply that out. Let me know what you get for Q. Don't forget to square the bottom, right? The bottom is squared. That's the H plus concentration squared. So please give me a Q. So punch that out. It'll wake you up, I guarantee. Like a slug of coffee, a little slug of chemistry first thing in the morning. Okay, and we got one answer already. It's 987 million. Okay, so yeah. Good. And you rounded it well. Good, Chelsea. So she's got. I'm going to change it to sig fig. So let's do 9.87. So she's rounded it nicely. So I got good sig figs times 10 to the what power? Nah, I think your power's off, Amina. Punch it out again. I think Chelsea's got it, but what power would that be? Minus eighth? Oh, no. It's going to be positive. It's going to be a big number because I'm dividing by negative fourth power squared. And then that, when I divide by a negative power, it becomes a big number for the total answer. So this is negative fourth squared. And I'm dividing by that. So it'd be like negative eighth, but it's going to be then positive eighth times all this stuff. You know what I'm saying? Punch it out again, folks. Thank you, Ellie. To the sixth. Chelsea has it as well. So to the sixth. Q has no label, so that's it. That's what we needed. Okay, here we go. Let's punch it in. So get our new delta G. We get the standard one, negative 147 point, try and make that legible, sorry. 147.0 kilojoules plus R, which is 8.31 times 10 to the negative third. Kelvin, no, what is it? Sorry, kilojoules per Kelvin. That's our weird R label for this particular type equation. Times the temperature, and the temperature, they didn't tell us it changes, so let's assume it's still 298 Kelvin. Why do I assume that? Because I'm using all this data for standard, so that's 25 degrees C or 298 Kelvin. Okay, gotcha. Yeah, I know it's hard to see the board, believe me. Hard for me sometimes too. Times the natural log of this sucker that we just got, natural log of Q. So natural log of 9.87 times 10 to the sixth. And can all of you punch that out and let me know what we get for the new delta G. I'll read those numbers again for our studio audience. Here we go. Negative 147.0 kilojoules plus this whole thing multiplied, 8.31 times 10 negative third times 298 times the natural log of 9.87 times 10 to the sixth. Let me know what you get. Let's compare and see. I'll wait for your answers. Please do this. You've got to make sure you get the same answer as everybody else. You got to be able to use your calculator with confidence and as speedy as you can do. And please go as quickly as you can. There, we got one. Thank you, Chelsea. Good. And she's rounded. I like it because I got 3 spots in my queue. I think that's about all I could get out of this. So negative 107. Let's see if others come up with the same thing. Yes, I'm getting others. Thank you very much. Good. Thank you, Louisa. Good going. So that is going to be kilojoules. No, it's going to be, yeah, kilojoules. Okay, now check this out, gang. What was it originally, the delta G? It was negative 147. So is this more or less spontaneous at this time? Thank you. Good. Everybody's got it. Good. Thanks for punching. Appreciate it, everybody. New question. At these conditions, with this concentration of H plus and blah, 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 is it more or less spontaneous than it was? Here it was negative 147. Here now at the new conditions, it's negative 107. So is it more or less spontaneous? So, spontaneous than before. So fill in the blank, please. So it's spontaneous than before. So is it more or less thermodynamically favorable? More or less spontaneous? Let's see if we got some answers. Oh, they're punching them in. I like it. I like it. I like it. And everybody's right. Now you guys are cooking. You're going to be so awake after this class. Less is correct. Why? Because negative means spontaneous, and this is now less negative. Look, the other one was negative 147. This is less negative, so it's less spontaneous. Well done, everybody. Good thinking. Thank you. Thank you very much. I love it. Okay, so we're going to stop and review and see if you got any questions. Everybody got that? Oscar, Bella, Amina, Alicia, I love it. Thank you so much. So let's review and say to ourselves, okay, what does this all mean with these delta things? So here's what I mean. Let's write review. And on the side, we're going to write we're going to say, what if this is negative, and then what if it's positive? And we're going to take delta H first. Make ourselves a little table. Okay, if delta H is negative, we say it's exothermic, like burning paper, right? And if it's exothermic, that tends to favor the products. So obviously, if it's positive, then it's endothermic. We knew that already at the start of the year, probably, most of you. And that favors reactants. I'll start to abbreviate now because I need to. Okay, so let's do now delta S. For delta S, if it was positive, that's when we got more, if it's positive, gang, we got more entropy, and that's favorable. So positive ends up being favoring the products. So that's going to be spontaneous, okay? And here, this one was spontaneous, so this is, sorry, for delta H, it was the negative side, which is spontaneous. Okay, so delta S favors products, and here if delta S is negative, it favors the reactants. Favors reactants, and it's non-spontaneous. Okay, finally, you guessed it, Chester. We're going to do delta G. We're going to do it in green for G. And we just said if that's negative, of course, it is spontaneous. We just did a problem with that, and of course, it's going to favor the products. I'm going to make more products if it's a negative delta G, whereas if it's a positive delta G, it's non-spontaneous, non-spon, or non-thermodynamically favorable, say that 10 times, which favors the reactants. So that's your little nice review chart for this particular chapter, okay? Helps you keep straight what delta H, delta S, and delta G, how they affect your reaction. Remember, am I making more or am I making less? Am I making products or reactants? Spontaneous, not spontaneous. You can't even see my other arm. Spontaneous, not spontaneous, okay? That's what this is really about. Okay, while you're writing furiously, let me blow my nose. And catch our breath. We'll probably be able to finish this chapter on Wednesday, even if we take your questions for half the period. But I want to start with something new. Let's talk over at the right side here about the relation between delta G, standard, and K, big K, the equilibrium constant. Now, recall, because I know I haven't seen you since before break. Well, I don't see you now, but if I could see you. The red row favors reactants, non-spontaneous, and favors products, spontaneous. Yeah, favors reactants, non-spontaneous, favors products, spontaneous. Antonym for the red row. Okay, relation between delta K. So recall, for K, if K is bigger than 1, it'll favor what? Do you see where I'm going? I bet you do. Who remembers? If I got a big K greater than 1, it favors what? What does a big K favor? What side? Products or reactants? A big K favors what? No, it says spontaneous, and Sophie. Delta H, spontaneous and exothermic favors products. Thank you, Antonine. Products. Oh, I got half of you do products and half reactants. Okay. I've got to go back and study that. If it's a low K, it favors the reactants. If it's less than 1, boop. Why? Because K was products over reactants. So if I got a lot of products, I got a K that's bigger than 1. If I got a lot of reactants, the fraction is bottom heavy and it's a low number, less than 1. So if it's bigger than 1, I definitely got products favored. Okay. So as you could guess, there's going to be a relationship between K and delta G. So definitely K is greater than 1, delta G is negative. K is less than 1, delta G is positive, okay? Non-spontaneous. So this is spon, and this, if delta G is positive, K is less than 1, is non-spontaneous. And this is really what chemists want to know, gang. Do things happen or are they not happening? Good. We're going to start with that relationship on Wednesday once we take some of your questions. So please work hard between now and then and have your questions ready from the book questions, chapter 2 and 3. Okie dokie. So I wish you a good week until Wednesday. Write me if you have questions, either on the group chat or Google Classroom or email. Okay? So I want you to achieve. We're going to do everything we can to accomplish that. I'll try and answer all your questions. Okay? All right. Thanks, everybody, for coming. Bye.